Hello and welcome to Go for Launch. Today, Audrey and I are joined by Ramy El-Maarry. Welcome, Ramy.
Hi, Mackenzie. Hi, Audrey. It's a pleasure having you today online. My name is, just for the listeners, I'm Mohamed Ramy El-Maarry, and I'm an associate professor of planetary sciences in the Earth Sciences Department at Khalifa University in Abu Dhabi.
We're really happy to have you on today. And before we dive into it, can we have you just tell us a little bit about yourself and about your current role at Khalifa University?
Great. Yeah, sure. So I'm Egyptian by birth. So I was born in Cairo, Egypt. I did my bachelor studies actually in Egypt, Faculty of Science, majored in both geology and chemistry. And then I did my master's and PhD in Europe, focusing more on planetary science and space technology, getting my master's through an Erasmus program in France and Sweden. Then I did my PhD in Germany in the Max Planck Institute for Solar System Research. Uh, Followed that up with a postdoc, as we academic usually do when we're still trying to find a job in the academia. Uh, Went to Switzerland, University of Bern, spent there 5 years, which were probably the springboard for most of the work that I've done, in particular with comets, which probably we can touch upon later. I followed that up actually getting a grant from the Swiss National Science Foundation to spend a couple of years in Boulder as a visiting researcher at LASP, the Laboratory for Atmospheric and Space Physics in the University of Colorado. That was a really nice bridging moment going from Switzerland to Colorado. Wasn't actually that much of a transition. You still had the snow, you still had the mountains, but you had all these uber athletic people in Boulder. And as Mackenzie knows, Boulder people are very, very sporty. They're really into their sports, into their healthy eating habits, their political views as well that are sort of uber liberal. So it's a very interesting bubble when you compare it to the rest of the United States. It's a really special place. Followed that up. I spent a couple of years in the U.S. and then I went to the U.K. where I got my first faculty position in Birkbeck, University of London, uh, in the Department of Earth and Planetary Science. And this is what the time during COVID, when I think this was really rough time for everyone. There was probably a year or two there where things were kind of tricky in a sense that we got to learn how to teach and during online and have to deal with all the sort of distance learning and all that. Obviously this was a pretty tough time for everyone. It's actually during that time that I got to know more about the UAE and what it was doing. So they were very clear in their ambitions of developing a space exploration program, something that I had a keen interest on, given obviously my heritage being from the Middle East and knowing how hard it was to actually uh, get a space science education. While being in the region. I mean, I had to, as you can see, I had to take some sort of a scenic route to get to become a planetary science. So when I heard that Khalifa University in particular was opening a bachelor degree in planetary science and they wanted someone to help set this up, it was something that I got really excited about because I envisioned hoping to do something like that at one point. I've been all around the world. I had been all around the world basically in the past 15 years, and I figured this was much closer to home and was a really great opportunity to take all that expertise, all that experience that I've acquired, kind of teaching and working in around three continents, and bring this back sort of to Khalifa University and help set up this planetary science program. So I've been here at KU at the Department of Earth Sciences, which now offers a bachelor degree in Earth Planetary Science. I've been here since and late 2020. So it's been sort of 5 years now, and just time has flown. I can't believe it has been actually 5 years. So that's a pretty long answer to your short question, Audrey. I hope I sort of summarized my life in 4 minutes.
Yeah, I would say that's a relatively short answer considering how much it sounds like you've done in your career and on your journey, and we're really excited. We'll have lots of questions for you on that, and we'll start off by asking what got you interested in planetary science in the first place? What sparked your passion in this field? And how has your journey led you to work with major space agencies like ESA, NASA, and then the UAE Space Agency?
I think my fascination was just books and cartoons when I was a young child, and as any other child, I just couldn't pick. I was really fascinated by two things, which is like very common for boys, I guess: space and dinosaurs. I had no idea what to choose. I loved actually both. I loved geology and I loved space. Uh, I remember as a kid, like building sort of models of. I had like sort of a school project that I just built at home. Kind of going through the entire geologic time scale from the Cambrian to the recent time, building sort of props and stuff with an ice age and dinosaurs and all these sort of things. And really up to high school, I was just really fascinated by both just geology and space and couldn't really pick. It's only I really distinctly remember I was in high school looking at that was the first time we actually get to study geology. That was obviously I'm talking about the Egyptian curriculum. Uh, and there was just one page in the science book, in the geology book, that was just kind of nonchalantly saying, "Oh, by the way, you can kind of combine geology with other scientific disciplines. So if you combine chemistry with geology, you've got geochemistry, and then there is a mixture of geology and physics, and that's geophysics." And there was just one sentence said, "Oh, and by the way, if you combine space with geology, there is a science called planetary geology." And I was like, "Whoa, is that something that combines both? This is exactly what I'm going for." So at high school, I had sort of made that decision, and I said, "Okay, so I can't study planetary science directly in Egypt. In fact, there's probably 4 or 5 places in the entire world where you can do planetary science on a bachelor level, Boulder probably being one of them." And I said, "Okay, so I'll get to the Faculty of Science." And that was sort of a kind of a cultural rebellion, if I would say, because in Egypt, people are expected to either be engineers or doctors. That's what you try to aim for. These are like the top jobs, but no one goes into Faculty of Science unless they've been rejected because they can't get to medical school or they can't get to the engineering school. So sort of the misfits that go into the Faculty of Science. But in my case, it was like the complete opposite. I said that I had actually the marks to get to the top schools in Egypt. Said, no, I'm going to the Faculty of Science. And it was such a bizarre choice at the time. And I'm saying so it was 1998. That even I think the first day at school I was in university in Egypt, it was such an uncommon thing for someone to go into the university by choice in Egypt that I think even the dean was passing by and was looking at the batch of first year students. And believe me, like in Egypt, it's I mean you probably saw some big classes in Boulder in the US. But like the freshman year for Faculty of Science in Egypt in Cairo University, which is like the biggest university, you're looking at like 1,500 students just as a freshman. And that's for science again, like the reject. Like if you go to the Faculty of Commerce, you probably see like 5,000 as a starter.
Oh, wow.
So the fact that there were like 1,500 students, and the dean said, "I heard someone here has entered universities kind of willingly with 98%, because that was like the percentile that I got in high school." It was like, I said, "Yes." I said, "Oh, I just wanted to make sure that someone actually did that." So I was kind of famous as soon as I got into the university. But yeah, I just really was fascinated with that sort of science and things like you hear books, you read books, you watch television, you get really excited about space stuff. You read stuff by people like Carl Sagan, and you get really excited. Cosmos was one of the things that I really loved growing, and even by the time I was in university, I was already kind of reading into nature and science, trying to get as much as I could from planetary science because I was still just trying to learn the basics. And obviously, a major, I would say, like a major bedrock that has allowed me to do this was the fact that my family also supported this, which is not something that tends to happen a lot. Like, are you like crazy going to Faculty of Science when you could do all these brilliant jobs, secure jobs? And said, no, no, this is what I want to do. And I really appreciate that they supported me in that, because probably without that, it would have been very difficult, particularly where I come from. And so what I've been trying to do through my journey is try to kind of change that stigma. Whenever I go to Egypt, I give lectures, I do a lot of public outreach events, talk to the students, talk to the kids, talk to the children that come with their parents, talk to the parents about my journey, because it really helps. And it has been quite fruitful to see how this has inspired a number of students to go into that field. It has helped a number of parents to kind of ease into that decision and help their kids pursue the things that they like. Because every time I hear this always from the students and from the young people. What should I do? What should I do? And I always tell them, like, you need to go for what you like. It's not just particularly at space. You need to go into what you like, because if you do that, then there's a higher chance of you excelling. That there's a higher chance of you standing up when you go through the failures. And you can stand up to the challenges, and you'll be able to hopefully excel in what you do.
Yeah, it's wonderful to hear an example of someone following their passions. And like you said, I think that family support, it sounds like it made a big difference for you. And it's really cool to see you paying it forward and trying to get younger scientists, younger students to follow that unconventional path if it's what they love. And when we were chatting about your background, you talked about your postdoc and some of the research positions that you had throughout your career. So can you talk more about how those have related to your work with the space agencies that we mentioned, like ESA, NASA, UAE Space Agency?
Yeah, I just really love and appreciate about my sort of journey in planetary science is I almost never planned for anything. And basically what I had planned for wouldn't materialize. And all the major events that happened seems to have happened by chance,
Mm-hmm.
in a way. Uh, so I've been like sort of on kind of on a weird journey, like in the sea on a raft, and just seeing where the current takes me, basically.
Mm-hmm.
Uh, the How it started for me with particularly space exploration and missions is, well, if I go back to Egypt, as soon as I had finished my bachelor degree, I obviously tried to find a master's to do planetary science and space science, and I tried for almost 2 or 3 years to do that, because obviously it was very clear that I had to travel abroad to do that. And in order to travel abroad, you need to pay for applications, you need to do GRE exams and all that, TOEFL, prove that you can speak English well, and all that stuff. And the applications take some money. So I would like work side jobs, things not particularly related to science, just to kind of cover the costs of these applications. Because again, coming from Egypt was not particularly a cheap thing to do. So I would apply to a variety of universities. Apply like for university I thought that was the university that really had a strong space program that I knew of at the time. So I would like to apply to University of Arizona, University of Hawaii, University of New Mexico. I didn't really think about Europe that much very early on, and I will sound really old, although it's not that I'm not that old. But it was during that time, like in the early 2000s, that people were talking about, wow, there is this new search engine called Google. I was like, whoa, okay, what is that? So it can help you like find things. And again, it's just a testament to how fast all the technology flows. Like I can talk about this and sound really old when really I'm not that old. And I remember just, okay, let's try this thing. What does it do? And I said, okay, a space program, masters in Europe. I said, okay, why am I always looking the US? And it's very tough for US university to accept international students on sort of an Egyptian degree or a degree that is not easily transferable. So I figured maybe, okay, let's try a luck in Europe. And I said, okay, what happened? I'm challenging you, Google, space program in Europe. And it actually turned out it generated a result, which was a program that was just starting for the first time. It's called the Erasmus Mundus program, called Space Master. It's just a fancy name, just in its own right, and it's so easy for a search engine to pick. It was the first time this program is going, and it's been really successful. It's been ongoing since then, since 2005. That's when I actually I applied to it and got through and got accepted. And it was such a cool idea that generally you get to see in Europe these Erasmus programs. It's not just for space science, but it covers like 70 or 80 different master's programs where you get to travel and study in different universities. It's sort of usually a consortium of 2 to 6 universities, where you get to spend kind of a term in each different university in a different European country, which is something you can do, obviously, because it's the European Union, and it's such far more consolidated in terms of the areal extent. Like the entire Europe is almost smaller than continental US. So you could like spend one semester in Germany, another one in Sweden, another one in France. So in a sense that every university in the consortium kind of gives you the best they have, the thing that they do the best, and you get just exposed to all these different cultural, educational systems. And it's just, I love the idea. And I said, okay, great, let's apply for this. And I was really lucky and happy to get it. So I studied like one semester in Germany, one semester in Sweden, in Kiruna, north of Sweden. Got to see snow for the first time, as this is an Egyptian, and see what minus 30 degrees Celsius. I don't know what that would be in Fahrenheit. Would be still really cold.
Very
You need to
cold,
do
yeah.
yeah. So minus 30 Celsius. And then I spent the second year in France, in Toulouse, which again is a pretty big place when it comes to space science and rugby, which is something that I like as well. And in Toulouse, I that was the first time I got sort of into planetary science, really, because yes, I was studying this, but I was kind of fortunate. I was looking for the sort of the project that I would have to do as a master's student, and given that I was in sort of an astrophysics program, that's kind of what I was doing in Toulouse, as part of the Space Master program. Uh, one of the supervisors was really keen on getting me on board because he saw that I had a background in geology, something that is not what you tend to see. So they had there in the university, they had students from the program, but they also had your typical French students that are doing this regular 2-year program. And all of them are coming from this sort of physics, astrophysics, strong mathematical background, but not a geology one or an earth science in general. And he was part of the science team on the Mars Odyssey. It's a US mission managed by NASA, but he was one of the French team members working on an instrument there, the GRS, the gamma ray spectrometer, looking and studying the surface of Mars, looking at the elemental composition. That's what that instrument does. It doesn't tell you sort of what sort of mineralogy you have on the surface, what's the composition, but it gives you, like, in terms of the elements, how much of every particular element you have, and then you sort of have to put in your your geologist and geochemist hat on, and try to figure out, okay, based on these elements, what sort of mineralogy would you expect to see on the surface? Uh, so that was the project that I first got involved, first on kind of being on the European side, but it was an actual NASA mission, and it was such a great opportunity for me to work on that as a master's student, and I really fell in love with, not just, I was already in love in planetary science, but now working on a space mission and looking at data that is sort of brand new and always kind of breaking new grounds is something that I really got fascinated with. And so when I finished my master's, I looked for a PhD, which by now was relatively easier because now I had a master's from a European institution. So rather quickly, kind of in just 6 months, not 3 years as happened with the master. So I had like a gap of 3 years between my bachelor and master's until I had found something. So I hope I wouldn't have to wait that much for a PhD. it was just 6 months, just the interviews and the stuff, and I got accepted, got a scholarship through the Max Planck Society, which again is a major scientific consortium in Germany. Again, not just planetary science, but you have around like 60, 70 Max Planck Institutes scattered all around Germany doing all sorts of things. You have the Max Planck Institute for aeronomy, you have the Max Planck Institute for geochemistry, cosmochemistry, biology, all sorts of things. And they have the Max Planck Institute for Solar System Research, which is currently in the city of Göttingen in Germany, but at the time it was sort of in the middle of nowhere in between two villages in an area called Katlenburg-Lindau. So it was kind of south of University of Göttingen, very close to University of Göttingen and Braunschweig, two major universities in central Germany. So I got accepted into that program. And again, being at Max Planck Institute, which was an institute that's very connected to a variety of ESA and NASA missions, that I got again through my PhD to work on another US mission, which was the Phoenix mission, which is again a Mars mission that went to the higher latitudes on Mars to look and study the near surface ice in the circumpolar regions on Mars. Most of the missions that land on Mars tend to do so in the equatorial regions because there's far more interesting things to see in terms of the history of liquid water activity and looking at interesting geology, but also the fact that because it's equatorial regions, it's sort of a lower elevation and it's somewhat easier to land in. So NASA also, you always have to think with any space agency, not just NASA, you always balance the science with all of the engineering constraints and how safe it is to land. So it is not easy to land in higher latitudes, and the Phoenix mission was one of the first ones to do this successfully because there were other failed attempts like the Mars Polar Lander, for example, that didn't unfortunately get going and land, had some issues. So with the Phoenix mission, I was again involved in a NASA mission. And this was in particular one where the first time I was involved in a live mission, like I went to the US, worked with the team. We would operate the instruments, look how, and I can see how you sort of plan a day to day during a space mission. Interestingly, for the Phoenix mission, sort of like a tidbit thing, I think there was a separate study being carried out, a biology sort of experiment, if you will, carried out with the team members of the Phoenix mission to see how they coped and their body would react to the differences between a Martian day and an Earth day, because obviously Mars has a much longer year. It's almost double the year of the Earth. But the Martian day is not exactly the same, but it's very similar. So it's just a difference of 40 minutes per day. And many people that would be working on a Mars mission, they actually want to change their sleeping patterns sometimes to match this so they can properly do it, which you can probably do with a mission that would only is expected to be operational for 2 or 3 months, as Phoenix was. So a lot of people were there like putting like plastic bags on their windows because every day they had to like sleep a little bit more just to and sleep for a slightly later and start the day like 40 minutes later every day almost just because of that offset they had with the Martian days. So there was like a study looking at that. I wasn't part of it, but I could see people doing this. So it's just an example of the weird things you get to see when you're on a space mission. And from that point on, it's really where one mission led to another in a sense. So I worked on this Mars Odyssey mission for my PhD. I got to work as well with data from other orbiters. When I went to Switzerland, worked with Nick Thomas, who was really one of the prominent European scientists and one of the top cometary scientists in the world. I worked at the University of Physics with him there, and he was involved in a number of missions, NASA missions like the Mars Reconnaissance Orbiter. So I kind of got involved with this. And up to a certain point, I was just doing Mars stuff. I was really happy doing Mars stuff, and that was it. I wasn't really planning on anything else. I said, yeah, Mars is just enough for me. It's my favorite planet now. I'm just going to look at this and continue to do this. And it was around like 2015 when a mission called Rosetta, which, as it happens, my boss was kind of involved as well because he was a member of the science team, and it was a mission that had sort of taken off in 2004, and it's been just wandering in space for 10 years because it takes that amount of time to get to a comet. It was a cometary exploratory mission, looking at a comet called 67P Churyumov-Gerasimenko. It had flew by a couple of asteroids on its way, but it had finally reached the comet in what was it? So around August 2014. That was the time when I was in Switzerland. And again, most of the science team were cometary scientists, primarily coming from a physics background or an astronomical background, like doing Earth-based observations. Most people that study comets, they do so using Earth-based observations, maybe Hubble and James Webb right now, but classically Earth-based observations. So again, this was sort of the core of the science team. And then again, I find myself in the physics department because of my work that I've done before, my background, and what I've done for my master's. But again, I'm sort of the geologist in the physics department. And Nick comes in to my office and says, "Do you want to take a look at some of the pictures of the comets? Because this is really great. We don't have these sort of pictures from a comet before. This never happened before, and we'll probably need some help to understand what the hell we're looking at." So, okay, yeah, what's cool? Let's see. Comets, all right. I've taken pictures on I've seen things for asteroids. Said, yeah, okay, yeah, it's interesting. I think I'm gonna stick to Mars. Uh, and then I look at the images we get from Rosetta, and it just blows my mind because you look at images from Comet 67P, and it's unlike anything else I've seen on asteroids or on small bodies. The behavior, how comets that their journey coming in from the outer solar system as a dynamical complex journey to make it into the inner solar system, the fact that they're just active when they get close to the sun, and you have to understand why they do this, you have to understand why they get active, and you try to just make sense of how weird the surface looks like because there's just no analog for this on Earth. There's no blueprint. So they're looking at me. So you're the geologist. What are you seeing? I'm saying, guys, there's no such thing on Earth. This is very strange. Um, there are some similarities, but there are things that are really weird. And up to this day, we still scratch our heads when we look at some of the features on Comet 67P because we still have no real solid idea how they formed and how they've evolved. There's a lot of still open questions. And again, I just suddenly worked on Rosetta for 2 years and I just fell in love with comets. I said, okay, sorry, Mars. All right, this is sort of my fling now. This is my new thing now, and I have to look at this now for some time because it's just super exciting. And so I kind of took a hiatus from Mars for 2 or 3 years, just doing cometary stuff, and just really fell in love with it. Most of my academic career has kind of went sort of 180 degrees from doing Mars stuff to cometary stuff, and then kind of stabilize around, okay, I guess I like icy landforms, so I'm going to be doing this now. So I'll do icy processes and landforms across the solar system because this is now what I kind of like. So it's kind of a really nice evolution of just kind of where the tide takes you, where certain missions have taken me, uh, that I just found myself doing all sorts of these things, which is it's amazing space exploration. Sometimes you can't really plan for what you'll be doing in the next 2 or 3 years. You can't really expect what you'll be looking at. You go into exploring a body, you have no idea again what you will expect to see, and you have no idea where that path is going to take you. So I did that work, for example, on Comet 67P, and then I left Switzerland. I went to Boulder. That's where I got during actually my time on 67P on Comet on Rosetta mission. There were at least three. This is an ESA mission, but it had a heavy NASA involvement. So there are like three instruments on the Rosetta mission managed by U.S. colleagues. One of them was Alan Stern, who was the PI of the ultraviolet spectrometer, so a special spectrometer that looks at the comet in ultraviolet radiation, and that can give us a lot of information about the plasma environment and how the comet interacts with outer space and the solar wind, for instance. And as it happens, he was the PI for a mission that probably you'll know really well, which is the New Horizons mission, which explored Pluto during the time when I was really heavily involved in Rosetta. But then for the follow-up mission, they had to fly. They were flying by a very unique object we've never seen before, a Kuiper belt object, a very small Kuiper belt object, what we call cold classical, beyond Neptune, far beyond any other spacecraft has explored, except for the Voyagers, of course. But this was going to be the farthest flyby of a small object, and I don't know when we'll be doing this again. So again, this was sort of the time that I didn't really plan for this. Happened to be in Boulder, and I was just going to move to the UK, but I had already got acquainted with Alan, and during our Rosetta time. I spent a couple of years in Boulder, so I got to know the people there a little bit more. And when the time came, Alan just graciously said, "Why don't you just come in and join the team, sort of as affiliate scientist during that flyby?" I really kind of asked him, "Alan, can I please come in?" He said, "Yeah, sure, come in." It was so gracious, and I was just really happy and excited about this. So at the time, I was in the UK, so I traveled back to the US for the flyby and got involved with the New Horizons team. And again, it was just sort of a out of body experience looking at this body for the first time. You lay your eyes, you look at the data and say, we are the first humans to lay eyes on this body that's been sitting there for 4.5 billion years, completely minding its own business. And it completely just, again, shatters our ideas of what we would expect to see. It doesn't look like an asteroid. It definitely doesn't look like a comet. And it's actually the closest we'll get to seeing what a small body looked like, what a primordial planetesimal probably looked like in the early solar system. So I'm just rambling about it. I mean, this stuff really gets me excited. So that's I didn't really plan for which missions I would get into or get involved with. It's just being in the right place at the right time, I guess, for most of the time. And it's been an amazing journey, really.
Yeah, it sounds like it.
Absolutely. I mean, you've literally studied things from across the entire solar system, even those Kuiper Belt objects that are technically part of it, but so unbelievably far away. Do you think, because this is just like my personal curiosity, since you've had so much time in planetary and then gone into the icy bodies of comets, do you think at some point you'll kind of mesh those two and go into the ice giants, Neptune and Uranus?
Oh, I don't know. We'll see. Uh, the science community is really pushing hard for missions to Uranus and Neptune. I think
Mhm.
they're the ones kind of missing now from our gallery of exploration of the entire solar system. And it's really amazing that we haven't gone back to them. You can tell, you can say the same about Venus as well. So Venus, Uranus, and Neptune, they've been like the least explored kind of. Even Mercury now, we've explored Mercury with the Messenger mission and with there's Bepi Colombo, all on its way. We're hoping very soon as well with the Envision and mission, and I think is it Da Vinci. Um, was it? I think I'm losing the name. I know. I don't think it's Da Vinci. It's Envision. What's the second Venusian mission? Envis.
Mm.
Hopefully these are going to explore Venus, but Uranus and Neptune, it's just they're just out there. It's very hard to get to them. It takes a lot of time, and you've seen that already with Pluto. In order to get to Pluto, which is like the outer solar system, if you want to get there in a reasonably fast time, you have to go really fast. And because it's always a trade-off in terms of the mass, how much fuel you put in there, and how much science you want to do, uh, if you spend a lot of energy to speed up, you have to spend a lot of energy to slow down. And that's kind of the main reason. Like, in order to get to Pluto in roughly 6 or 7 years, I can't remember how much it was, but in order to do so, it meant that it was impossible to have enough fuel to slow down enough to get captured by the gravity of Pluto and go into orbit around it. So it's sort of such a trade-off that you need to do. So again, with Pluto, you say, okay, I'm going to do a flyby because this is the best I can do. If I want to go orbit Pluto, this is going to take forever. And Uranus and Neptune are stuck between like this, a hard place and a hammer. So what do you say? You want to explore them in a much better way, much more efficient way than you've done with Voyagers, but that would mean the missions need to have a lot of fuel, or they need to take an extremely long time to get there and explore them, and that's why it's been really hard, despite Uranus and Neptune consistently being top priorities in every decadal US NASA decadal survey you get every 10 years. They're usually close to the top. It's just really hard to implement a mission in a conceivable amount of time with the right amount of resources to get there. I'm hoping we'll do it one day, but I think it's going to need a substantial jump in our launching capabilities and how much sort of fuel we use and sort of technology that we use to get there. Because we need to get there in a reasonably fast enough time, and I question whether we still have the technology to get there, not just in a fast way, because we can do that. We've done that with New Horizons, but also in an efficient way that allows us to get into orbit around them. I think this is really the challenge with these two planets.
Absolutely. They're so unbelievably far away. At least you do have a little bit more gravity to work with than you would on Pluto. And since you mentioned Venus, I think one of my favorite stories about planetary exploration is how we used to send things to the surface of Venus. And we have since stopped doing that because everything just gets crushed and melted immediately. So now we just get to look at it from space. But speaking of all of this technology and progress, specifically in the Middle East and the UAE, can you share what the UAE's vision is for the future of space exploration and perhaps other scientific research opportunities that are coming up?
Yeah, so for the UAE, I think the major vision started around 2017, when they started to think about the mission, which is the Hope mission, the Emirates Mars mission. But at the time, there was also the sort of 100-year initiative where they decided the UAE should have a colony on Mars by the year 2117. So the year looks like just a random number, but it has to do with saying in 2017, okay, let's try to get there in 100 years. And the space exploration program for the UAE is started with the with the Mars Hope mission. That is currently in orbit around Mars, and it's an atmospheric mission, primarily focusing on the atmosphere of Mars and trying to understand how the atmosphere evolved, how Mars lost its water. Did Mars have a much thicker atmosphere, and how did that happen to evolve? How did we happen to lose that atmosphere? And in fact, it's a mission that has a lot of parallels and a lot of interesting synergies with the NASA mission, which is MAVEN, which is also studying the atmosphere of Mars. And there's a lot of similarities between them and a lot of points of synergy. But there are actually two other important programs within the space exploration program, which is the lunar exploration program, which is primarily managed by the Mohammed bin Rashid Space Center in Dubai, and by extension the UAE Space Agency, where we're trying to build a small lander, a rover that would investigate the surface of the moon. We've tried to do that for the first one. Our first attempt was in 2024 with the Rashid Rover 1. And with this particular program, we rely obviously on collaboration with international entities, particularly when it comes to the launching and landing. As you know, the for the moon in particular, this is an extremely challenging aspect to do, in particularly if you do that through private companies that are still trying to build up that know-how and technological know-how. And we've seen obviously with the space sector how things are rapidly moving now, because you are getting all these major space startups and private companies that are kind of taking over a little bit from the national agencies and getting things done in a much quicker and efficient way, which has sort of given all this space exploration kind of a really nice boost that's needed, particularly when it comes to lowering the costs of launching, as SpaceX, for example, a prominent company has done, which is something that obviously we look at with a lot of interest here in the UAE. So we tried with a private company to land back in, I think, in 2024, and unfortunately the landing didn't materialize, and we were just on board the launcher and just basically lost our rover before it ever touched the ground or had the chance to even contact it. So we've been working on rover 2, Rosetta 2, and hopefully there are talks of having another one. But now we are set on having Rosetta 2 to land hopefully in 2026, where it's gonna land somewhere close to the polar regions of the moon, to look very closely at the ice in the permanently shadowed regions. So some people might realize that there's actually a lot of water ice on, not just on the moon, but even on Mercury, if you believe it. In these areas in the polar regions, you get these permanently shadowed regions, areas that are just never see the sunlight at all. And so physically, from a thermophysical point perspective, they act as cold traps that can trap water ice in these areas. So these are areas that are of extreme interest, not just from a science perspective, but also from a colonization and economical perspective. If you going into the point of sending people to the moon again and building maybe perhaps more long-term colonies on the moon, you obviously need a source of water. And this is something that is available in these PSRs, these areas on the moon. So this is something that we're keen on studying and investigating. So that's the Lunar Exploration Program. But we also have the mission that's probably, I would argue, is the most ambitious, which is the UAE mission to explore the asteroid belt. And this is a mission currently in preparation. We obviously have international collaborations as well. One of our major collaborators are the University of Colorado in Boulder, particularly LASP. And this is launching in 2028, would have a gravity assist with Venus and the Earth. And then we would have sort of a tour of the asteroid belt, if you may, of flying by 6 different asteroids, most of them being water-rich asteroids, because this is one of the core scientific goals that we have for the mission, is to understand more the water-bearing asteroids. How has that played into the formation of the planets and the solar system formation in general? And then we finish up with a very interesting asteroid rendezvousing around it, going into orbit around it, the asteroid Justitia. In all this, obviously, in the asteroid belt. And hopefully we'll try also to land a small lander on the surface of the asteroid, which is something we're also developing here almost in the UAE. So it's going to be a really interesting mission, launching in 2028 and going through probably the first flyby around the 2030s. And then for the next 4 years, we'd be flying through these different asteroids and reaching Justitia, a very interesting asteroid that some people think it might actually have originated from the Kuiper belt, and just made its way to the asteroid belt during the solar system formation, with all the things that are happening, particularly with the planets migrating and moving bodies all around. we think that there is a possibility that this asteroid may have actually come from the Kuiper belt. But we don't need to know for sure until we get there, when we study it more intently.
That all sounds really exciting, and it sounds like we're sort of lined up to learn a lot more in the next decade, and UAE is working on a lot of the advancements and the missions that will get us to that new knowledge. And it does sound like that in these missions, there's a lot of international collaboration involved. So how crucial would you say global collaboration is when it comes to advancing space technology? And what advice would you have to young people who are trying to enter this field right now?
Yeah, I think the entire space exploration program is built on cooperation, and it's always been, to me, one of the most noble human endeavors that you can think of. Ever since the space race in the 1960s, when there were major political drivers driving space exploration, since then, it has mostly been driven by just human curiosity and trying to answer really basic questions about how did the Earth form? How did the solar system form? What's the source of water on the Earth? How did life start? Is there life somewhere else in the universe? Do we have life somewhere else in our solar system? Uh, we've already starting to answer a few questions regarding if there are any other planets, because we're already discovering now so many different exoplanets. But because this particular science is driven by human curiosity, and is also driven by need to always break boundaries and find new technological solutions, it's it's just very productive, and would be extremely counterproductive not to do it in an international collaborative way, because everyone has something to provide. And generally, this you see, this has been the norm basically with space exploration ever since the, let's say, the 90s and 2000s. It's very it's really the more of the exception rather than the norm that you see now a mission being predominantly carried by one country. And because of that, you get this interaction with so many different people from around the world. In a sense, space exploration is also a really great way for universities and academic institutions to get involved in research. So it's a primary way as well, a primary motivator for universities and research institutes to be drivers of technological development and feed that as well into their education. And I don't think there is any other discipline that does this better than space exploration, where you get to actually get in universities involved, and by extension, students. So you can be studying at a bachelor level at a university and doing something related to space with your teacher, with your supervisor. Uh, you can't probably do this like with genetics, for example, or uh, computer science, or these sort of other disciplines. It's just very difficult. It's only with space exploration. It's one of these few sciences where you can get people at a young age involved and hooked very early. Uh, Space exploration, to me as well, is a wonderful tool for public outreach when you're trying to get people into STEM and to love science. Just you show kids a picture of a planet or something from space, and you're bound to get them excited, right? Much more than if you show them sort of a test tube or sometimes even a fossil. I mean, kids still love dinosaurs, but space is just such an easy way to get children involved and love STEM. So you not necessarily at the end up being planetary scientists, but you you spark that interest and that curiosity, because in a sense, all planetary scientists, in a sense, I think of us as people who just refuse to grow up. We're just children. We maintain that curiosity that we had when we were children, And somehow we've managed to maintain this, and we refuse to grow up. That's basically what a space scientist is.
It's so funny that you mentioned that. I do a lot of outreach for CU, and I always tell the kids that this is the coolest job in the world, the coolest field, because we are some of the only adults that do not have to get rid of their imagination or curiosity and be, just serious adults. We get to look up and just wonder all day long, and it's so exciting.
Yeah, so I would say again, just because I think I did not address that question. I obviously get that as well a lot. I mean, what do you say to kids? What do you tell them, or anyone who wants to get to that field? Never use your curiosity, never lose that. Read a lot. I mean, read a lot. Don't just rely on what you get in the school and your curricula. Obviously, you're building these foundations, but space exploration and planetary science is just an ever-evolving science. And if you turn your back on it for a few years, you find yourself way outdated. Uh, it's an exciting thing, but it's also a challenging thing from my perspective, teaching planetary science, that every single year I have to go over the slides and I have to remove stuff, add new things. And if I were to look at a course that I was teaching 4 or 5 years and compare it to what I'm doing now, and say, wow, okay, that's how far we've already gone. And it's not a one-off thing, it's just constant. If you're teaching a thermodynamics course, you're good. You build your slides and that's it. You're going to keep teaching that for the next 10, 15 years. That's not a problem. If you're teaching a planetary science course, you have that obligation and that challenge of actually changing so many things every year, so many different concepts that we thought we knew, and no, actually, this is not the case now. I mean, if we just, okay, what is the source of water on Earth? Then just in the last few years, we've gone from, oh, they probably come from comets. No. We don't think so now. I think where they come from asteroids, but no, not just any asteroids. No, there must be probably the water-rich asteroids, and it's just every few years. This is a sort of thing that we get to learn. We get to expand our horizons, and as an educator, it's an obligation for us to keep that curiosity going, but also to keep true to what is happening in the field by saying, by the way, this is not particularly the right thing because we may change it in a couple of years. This is now the most acceptable hypothesis for what we think is happening. And I don't think there's any other science where you can do this really. Sometimes things just change from. I start the course in the term and I said, okay, I told you something in the first lecture. We'll have to change this now. That's sort of thing that happens with when you're teaching planetary science. So for someone who wants to get into this, just read a lot, maintain your curiosity, uh, build up your soft knowledge of all sorts of variety of things, because a planetary scientist is really a jack of all trades. Uh, I come from that sort of background, and I know that most successful planetary scientists do not fall into one niche of just being physicists or chemists or geologists. They actually know a little bit of everything. And if you want to get into space exploration, you will have to sometimes put on your engineer's hat as well, because you need to have these constant dialogues with the engineers when you're developing a space mission, because there is this dialogue, this constant trade-off, like, I want to do this great science, and then you say, well, this is what we can do. All right, this is the budget, this is the mass budget, this is the money that we have, this is the fuel that we're going to use. So all these sort of different kind of breaks that you have, and you have to find the trade-off, the way to optimize this. So there is a lot of constant dialogue in order to get to that mission that launches with these sort of instruments that are going to do these sort of measurements. Behind this, there's just been a lot of compromise, a lot of constructive talking between the engineers and the scientists to get something that is grounded in what we can do, but also from the engineering perspective, pushing the boundaries in order to get as much science as we can with what we have. And it's actually through this that we get actually so many different engineering innovations that are just brilliant, not just for the missions, but you find out afterwards that these things have an interesting application that we probably didn't think of. And that's kind of what I also ask, because you get a lot of these questions of why are we putting money into space exploration? Well, why are we even spending money on this when we should be spending that money on something else? It always comes in when you have to talk about a budget or a national budget, any place in the world. Why do we do space exploration? And we do it because it helps with education. It helps with technology development. It's a driver for technology. It's a driver for economy. It creates a lot of jobs. It just does so many things. And on the long term, when you look at the technological advancements that we've had in the past 20 years, a lot of it is thanks to space exploration. And we can probably spend a couple of hours just talking about this. Your mobile phone, your internet, your solar energy, your solar panel energy, the whole point of solar panel technology is based on space mission. These thermal blankets that people use, that the fire stations use, and you cover people with it. These again are based on things that were done for the space program. One of the recent things that I've even read about is I didn't know, and it was actually a really interesting thing, is even the newest, like the LASIK surgery, the biomedical procedure to fix aberrations in the eye, in the lens of the eye, is again spawning from the technology that we've developed in order for satellites to actually dock with each other. So for the variety of space components to dock, they use sort of a laser guiding system. And this laser guiding system is actually, we thought about it, why are you doing this? And as it turns out, it actually has a biomedical application now. And you get into this, you have no idea where it's going to get you, but it's we've seen this so many times that it's undeniable. The technologies that we develop for space exploration, more often than not, have really positive, impactful ramifications on our current livelihoods.
Absolutely. The opportunities of this field are just exponential. There's no limit to any of it. I mean, I'm pretty sure even like Velcro, what you use to,
Yeah,
stick
yeah,
some
yeah.
shoes together, that
That's
came
true.
from
Yes.
space. The cameras in your phone did, all of it. Um, but since we've talked so much about all of the different things that you've accomplished and been a part of, quickly, before I let Audrey get to our last question, I heard you have an asteroid named after you. How in the world did that happen?
Um, well, there are far more asteroids probably than humans, so I'm not so sure which one is it me having a name on an asteroid, or an asteroid that's named after me. Well, okay, but the thing is, we've discovered so many asteroids, and we keep discovering all the time. So all of these asteroids have just astronomical designations. So what the IAU, the International Astronomical Union, tends to do, like every year, is okay, remove some of these sort of boring astronomical code names that we have for these asteroids that we keep on discovering, and use some of the scientists or notable people as names for these asteroids. And usually these tend to come as nominations from the science community. So some people are actually surprised to know that, for instance, if you discover an asteroid, you don't get to name it after yourself. You can name it after your wife if you want, or your girlfriend, or just a goofy Looney Tunes character if you want, but you can't name it after yourself. So in order to get something named, it's not that you have to discover it, but it has to be a nomination, usually by the community. And so what the IU usually tends to do, sort of in an annual way, is see the nominations, look at what people have done in research, and a subset of people are given this sort of honor of having some asteroids named after them. Generally, as well, most of it is usually kind of, let's say, reserved to people who tend to do work particularly in asteroids, because they're asteroids. But every now and then as well, if someone has done something kind of significant in a related field, they can be lucky enough to get their name on. And I heard about this nomination just before going to a lecture. I think just a couple of years ago, I got an email sent from one of my colleagues telling me, so an asteroid has been named after you. And I'm guessing it has to do with always what I've been sort of lucky to do, really, during my time with Rosetta, with all the work that we've done with in exploring the comets and doing a lot of research, particularly about cometary geology, a science that up to that point didn't really exist. And I think perhaps the science community looked positively on my contributions regarding cometary science, particularly focused on cometary science and cometary geology, and figured it would be a good idea to have an asteroid named after me, which obviously is something I'm quite proud of, but at the same time really humbled by it, as it's something I feel is rather than not just an honorable thing to have, but it's a driver for me to keep spreading that science and keep the excitement that got me to this point. I try to find a way to transfer this to the younger generation.
Yeah, it's even cooler, actually. I would have assumed that you discover something, you get to name it after yourself, but it's even cooler
No,
that this was a
we can't. That's
nomination.
the thing. Yeah.
Yeah, good to know. And congratulations on having that asteroid named after you. And if we've got any listeners who are into planetary science or are thinking about doing it, maybe that's even stronger motivation for them to really dive into the field and do some good work. You might get an asteroid named after you one of these days. And with that, we have come to our final question, which is something that we get to ask all of our guests. And that is, what is one thing that you're deeply curious about, something that you find yourself thinking about all the time, and that can be in your field or outside of your field, something we've already talked about or something totally new?
Yeah, I'm the worst person to ask this because, again, I'm just so curious about so many things. I think if you ask any planetary scientist, they're going to give you the same answer. We're just really curious about so many different things. Um, but I probably what is really currently, because I started kind of with Mars and then moved into comets, and from comets went into asteroids. That's what I'm doing now. So I've increasingly got more and more interested with solar system formation, how the solar system formed, and trying to just being very interested in these sort of big questions. And what is what is really clear to me now, when you have all these wonderful discoveries of these so many exoplanets now, so we've probably discovered more than, I don't know, 4 or 5. The numbers keep going. It's like 5,000 exoplanets now, thousands of exoplanets. These planets are in outer solar systems, orbiting other stars. Just for the listeners, so not just our solar system. And you look at these systems now, and somehow we've seen all these different planetary systems, and yet ours is somewhat unique. It's really unique. You look at all these different systems, and you have these super Jupiters and super Neptunes, and you have these weird Jupiter-sized planets that are so close to their stars, even closer than Mercury. You have a system that, and we get to a point where first we were just, okay, the observations were just allowing us to see just big planets, not the small ones. But now the observational techniques are improving, and we are getting to see what we would call our terrestrial planets, like small planets. And you have one of these systems, one of these amazing systems that have at least 3 or 4 of these terrestrial planets in the Goldilocks zone of its system, which means these are in the habitable zone. So there's just so many exciting things about this. And so I wonder so many things when we look at this. I say, are we gonna? Am I just gonna like wake up one day and see we finally have a definitive answer from one of these, that they've actually found a signature of life on one of these planets? Because we've been flirting with that idea for some time now, but obviously we can't have it's not there's a very tough it's not easy to get a definitive answer on this. And I wonder, will this actually happen in my lifetime, that we might actually see definitive answer for that there is life somewhere else out there? And just not ironic, but frustratingly, it's going to be very likely so far away that there's just no practical way of ever getting into that place or getting into contact with whatever this life form is. But it's going to just have really profound implications for how we see ourselves as a species, and how we see ourselves as a position in the universe. From a more academic perspective, what I find really extremely unique as well is, as I said, our solar system seems to be quite unique. We found now all these different systems with all these fanciful planets, the super Jupiters, super Neptunes, all these different kind of planetary, I say, alignments, where there's just also sort of different ways by which you see these planets aligned with respect to their star. But we haven't yet seen a system that is similar to ours, like in terms of, okay, you got terrestrial planets there, very close to the star, and then you've got your Jupiters and Saturn just right outside, and it's kind of the same, what we accustomed, and we thought that would be sort of the classical, this is how every solar system should look like. No, so that entire research for exoplanets has thrown so many curveballs at my community in terms of trying to understand how planets formed, and having worked so hard to understand how our own solar system formed, to realize that it doesn't necessarily work this way everywhere else. And in fact, not only this, but it seems like ours is more of the exception compared to the other systems. That is just such a fascinating thing for me to see, and I'm really interested and curious to see how this is going to develop in the next decade or so, because it's developing really, obviously, really fast. And what we're getting now with the James Webb Space Telescope is just mind-boggling. It's just amazing.
Absolutely. I agree. It's probably one of my favorite things about my job is that I'm paid to just know what people are doing all the time. What kind of new things are we learning? And I'm pretty sure I've joked about it before, but it's just an incredible source of job security. There's so many questions to wonder about and to answer all the time. But yeah, you have given us so much to think about. And thank you so much for spending all of this time with us today and telling us about all of the things that you've accomplished and giving us and our listeners something to look forward to. I can't wait to hear what else you do. But thanks so much for hanging out. And we'll probably hear about your future accomplishments soon.
Thank you very much. It's been an absolute pleasure.
Thank you. Bye, everyone.